Now we get to repeat what we just did with arithmetic sequences and series with geometric sequences and series. So in a geometric sequence, the biggest difference is that instead of adding something to the preceding term, you multiply something to the preceding term. So for example, if you have a sequence like 3, 6, 12, 24, and 48, you can tell this isn't arithmetic because from 3 to 6 is adding 3, from 6 to 12 is adding 6, it's changing. So instead, we want to check to see if there's something called a common ratio, which means that instead of adding something, you're multiplying something. So to find the common ratio, you take any term and divide it by the previous term. So to find the common ratio, we could take the second term, which is 6, and divide it by the first term is 3. We find the common ratio is 2. Same thing here. If we take any other term, let's say 48, if we divide it by the preceding term, which is 24, we still get 2. So this sequence, instead of having a common difference, has what we call a common ratio. So I want you to see if you can find the common ratio in this sequence. Pause the video, give it a try. All right, so hopefully you took the second term and you divided by the first term and you got -1/2. And again, if I took any of them, this one gets a bit more complicated, but just to remind you how to work with fractions. If we took -1/8 and we divided it by 1/4, I would rewrite that as -1/8 divided by 1/4, which is the same as -1/8 times 4/1, multiply across or simplify first, and we get -1/2. So no matter which two terms we take, we get a common ratio of -1/2. All right. Just like arithmetic sequences, there is a general formula for geometric sequences, but it doesn't involve addition, it involves multiplication. So how this works is that you take, to find the nth term, you take the first term and you multiply it by the common ratio a certain number of times. How many? Well, one less than the term number you're finding. So for example, if I wanted to find the 7th term of the sequence for 20, 100, I'd want to know the nth term. Nope, that's what I'm finding. I'd want to know the first term, which is 4, the common ratio, which would be 20 divided by 4, which is 5, or 100 divided by 20, which is 5, and the number of terms, which is 7. So then to put it into the formula, I always like to rewrite out the formula as many times as possible, then I have less chance of messing it up. I am finding the 7th term when the first term is 4, the common ratio is 5, and the number of terms is 7. So the first thing I would do is look at this and say, okay, this is 4 times 5 to the exponent 6. Now listen and listen carefully. What has an exponent of 6? Is it 4 times 5 that has an exponent of 6, or just the 5? The answer is just the 5. This is 4 times 5 to the exponent 6. If you think about BEDMAS, you have to do exponents before you multiply. The biggest mistake I see with this is people think they can do 4 times 5 and then do it to the exponent 6, and you cannot. You have to do 4 times 5 to the exponent 6. Okay, now you can plug that all into your calculator, and your calculator, of course, does our order of operations. Or you could do 5 to the 6 and then times it by 4, but just experiment with it. So I get 4 times 5 to the 6 is 62,500. All right, pause the video, and I want you to find the 10th term in this geometric sequence. So I'm going to start with that general formula. Okay, I'm finding the 10th term this time, so when n is 10. The first term in this sequence is 64. The common ratio would be -32 over 64. You want to put that in lowest terms, so 32 goes into both, so it'd be -1/2. So I'm going to put in -1/2 to the n minus 1, and so to the 10 minus 1. All right, so now I've got 64 times -1/2 to the exponent 9, and again, my calculator will do this for me. Now keep in mind, I'm going to try this with a calculator, but if I get a decimal answer, and it's not a nice decimal, then I am going to, sorry, I can't type and talk at the same time. I am going to do it in less steps so that I can show all my work. Oh, see, I can't talk. So 64 times -1/2 to the exponent. can't type this in, 64 times bracket -1 divided by 2 on bracket to the exponent 9. Whew, that was tricky. So I get -0.125. Now, there's nothing in this sequence that says that I should give fractional answers, so -0.125 is a fine answer. Okay, if I wanted to get a fractional answer, you could change this into a fraction, or you could go back here and say, hey, you know what, I'm going to do 64 times -1/2 to the 9, which means I'm going to do 64 times -1 to the 9 over 2 to the 9. So then you could plug in, -1 to the 9 is negative, so I'm going to get -64 over 2 to the 9 is 512, and then I can reduce. So 2 goes into both, and you just kind of take it until you get to the place that you're the lowest terms. So I'm going to get 64 over 512 actually simplifies to -1/8. And again, 64 goes into both, and so then you can just simplify, or just divide by 2, divide by 2, divide by 2, divide by 2. Totally up to you. But if you told me that the answer for the 10th term was -0.125, it's a great decimal. It's finite. It ends. That's what makes something a great decimal. If it was an infinite number, right, an irrational number, then I would definitely want to see it as a fraction. And even repeating decimals, I want to see as fractions as well. All right, the next thing. Finding the nth or general term. So what that is that you're going to plug into the formula a to the a base n is equal to the first term times the common ratio to the exponent n-1. And you're going to fill in everything but the n, right, which means we don't know the nth term. So you're going to keep it as a base n. The first term of this equation is -2. The common ratio I find by taking the second term and dividing it by the first term, and I also get -2. There we go, to the n-1. Now this is great, and if I was going to use this, I could keep it out of it. But the back of the book. The back of the book likes simplified answers. So if this is my general equation, I want you to look at the fact that this -2 is the same base. So this is -2 to the exponent 1 times -2 to the exponent n-1. When multiplying this powers of the same base, you can add the exponents. So 1 plus n-1, which would simplify to -2 to the n. Make sure you have the brackets because it's -2 to the exponent, not just the 2, but it does simplify to that. So I find that takes a little bit of practice. I was kind of thinking that when we were doing this guy, I was like, ooh, that would be a good one to do a general equation for, which is why I got a little stumbly with that one. So let's say we did the general equation with that one. What would happen? So this one's a little bit harder. Okay, so again, you won't know the nth term, but you do know the first term. So the first term in that sequence is 64. The common ratio we found was -1/2, and it would be to the n-1. This is a great answer. This is fine, but it's not simplified. It's not simplified because we can actually make the bases the same. So what if I wanted to write these both with bases of 2? Oh, no, that one wasn't a good example. Sorry, I just got distracted. So let's just say the common ratio is +1/2. I wouldn't ask you to do one that's -1/2 because then you wouldn't have the same base. So the common ratio would have to be +1/2. But this is still a great question. So what if I wanted to make these both have +2 as their base? Okay. What we'd have to look at is that 64, think back to your logarithmic chapter, right? We did this a lot. So when solving, powers that were a variable and you had to make the bases the same, 64 is 2 to the what? So 64 is equal to 2 to the what? You can use logarithms to solve that, right? Rearrange it. N is equal to log to the base 2 of 64. So you'd plug into your calculator, log 64 divided by the log of 2, and you end up with 6. Or you can just play with it, right? You could just keep plugging in 2 times 2 times 2 times 2 until you get to 64. That works as well. But 2 to the exponent 6 is 64. Now, what about a half? A half would be 2 to the -1. okay? Because 2 to the negative 1 would be 1 over 2 to the 1, and that's why it didn't work if this was negative. It just kind of flashed in my head when I saw that other one. That would be a good one to check. But if you end up with equations where the bases can be written as like a base 2 or a base 3, you should do it. So now I'm going to apply my power rule. I'm going to multiply these powers, so I end up with 2 to the 6 times 2 to the negative n plus 1. And now when multiplying powers of the same base, you add the exponents. So for this one, you'd end up with 2 to the negative n plus 7. So just saying, there's not that many examples of these to try, but it is an expectation at this point in Math 60 is that because you've done, the logarithmic chapter and you know the exponent laws, is that if I ask you to find the nth or general term of any sequence, then you can put it in as simplified a form as possible. All right, go give these a go. Sorry, my mouse wasn't letting